Okay. So, let us start, and what we have got is power needed, that is rate of energy needed is equal to Q into delta P. So, this equation, and we can write this as Q into rho G H L. So, both of these equations one can use for the calculation of power. Let us say for a pump, let us say we have got a pump, this is the representation of a pump. This is 1 and this is 2. So, from here we can get what is delta P. Basically, we neglect other heads. So, delta P is the main contribution of the pump as far as change in head is concerned. So, delta P from this 2 we will get this multiplied by Q. So, that will give you the power needed to run the pump. Okay. So, if you know delta P and if you know the volume flow rate, one can calculate what is the power needed to run the pump. And then we can use the second equation also. Suppose we have got a pipeline. For this we have calculated what is HL, this is L, this is D, all these we know, and we have calculated what is the head loss. So, in this case power dissipated we can get from this equation Q into rho G to HL. So, this is Q, flow is going through this pipeline. Okay. So, we can use this equation in different places as and when required. We can use this equation to estimate the power. Well, let us take one example where we will apply some of the things which we have learned. Let us say we have got a reservoir and in the reservoir we have put a siphon like this. Let us say this is H1, this is H2, and let us say this is H3, H1, H2, H3. The diameter of the siphon is D, inner diameter. In fluid flow through pipe, we are not interested in outer diameter. So, we are interested in inner diameter. And let us say L, total length of the siphon tube, total length of the siphon tube. Well, now what I want to calculate, that at this instant when this is H3, what will be the value of Q? I want to find out what is the value of Q. what is the value of Q. So, this is water and it is flowing through this tube. So, what is the value of Q? That is what I am interested to find out. Then I want to find out what will be the maximum value of H2 max. What is the maximum permissible value of H2 so that there is flow through the siphon. All right. So, first question is very important. So, how to find out Q? How should we approach this problem? Okay. So, basically this is application of Bernoulli's equation. Okay. Of Bernoulli's equation. Case 1, friction is neglected. First case, we are neglecting friction. All right. Then if I apply Bernoulli's equation, how should we apply? Between which 2 points we should apply Bernoulli's equation? Okay, that is also a good good suggestion. That means let me put point 1 here and point 2 here. Okay. When I am applying it between point 1 and point 2, what I am doing, mentally I am thinking, though I can write it here also, that there is some sort of an arbitrary streamline going from point 1 to point 2. That is what I am thinking. Okay. I can write that also, that assuming that there is a streamline between point 1 and point 2, I am applying Bernoulli's equation. Obviously, because the fluid has to move, and let us assume that a fluid particle that is moving along this path, and between point 1 and point 2 I am writing Bernoulli's equation. So, writing Bernoulli's equation between points 1 and 2. I can write P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2. It is very convenient to take Z is equal to 0 here, all right, because from here all the heights have been given. So, if I do that, I can write P1 by rho g, that is atmospheric pressure, P2 by P2, P1 is atmospheric pressure and P2 is also atmospheric pressure. So, I can cancel these two. V1 square by 2g, as the area here is very large compared to the area here. So, this velocity is almost equal to 0, or it is negligibly small compared to V2 square by 2g. So, basically this is gone, this I am putting, it is almost equal to 0. Z1 is 0 because here I have taken the datum plane. So, Z1 is equal to 0 also. all right. Oh, sorry. Instead of Z1, Z1 is equal to 0 and Z2, if right, Z1 is equal to, this is equal to, I can write, no, this is minus H1. My 1 is here, my 2 is here, so Z1 is equal to minus H1. All right. It is coming down from the datum plane. All right. So basically I can write, let me go to the next page, V2 is equal to root over 2G H1, root over 2G H1. Okay, root over 2G H1. Well, let me see this figure once again. So basically, let us say this is a fluid particle, okay, and let us take an analogy of solid mechanics. This fluid particle is at stationary condition, so it will have a potential energy compared to this datum plane. It will have a potential energy equal to what? mgh, and when it will come here, it will have a kinetic energy is equal to mv square. So if I compare these two, from there we will get v is equal to root over 2gh. So that is what we have got, because I have neglected friction. So as if a particle, just like a solid particle, it has moved through this distance without any friction, and the entire amount of potential energy has got converted into kinetic energy. So the corresponding velocity we have got. Now what V2 we have got, from here we can calculate what is the Q, and that is the flow rate we will get. So the first question is answered. Second question, what could be the maximum value of H? What could be the maximum value of H? You see, H2, sorry. If we calculate the pressure at this point at H2 corresponding to H2, we will get a pressure which is below atmosphere, or which is below atmospheric. Okay, we can do that very easily. So let us say this point we call as, this point we call as point 3. Then writing Bernoulli's equation between points 1 and 3. So we will have P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square, no, this is V3, no. So P3 and V3 square by 2g plus Z3. All right. Now we can write Pa by rho g, or plus 0 plus 0. V1 is very small compared to other velocities, so we have put it 0. Z1 is equal to 0. So P3 by rho g, V3 and V2 they are the same. velocity here and velocity here, they are the same because the pipe diameter is similar, I mean identical. So, we will have same magnitude of velocity, no change in diameter. So, what is V2 square by 2g? V2 square by 2g is equal to H1. V3 square by 2g is also equal to H1. Okay. I can write here just V2 square by 2g is equal to H1. All right. So, V3 square by 2g is also equal to H1. That is what I have written. Plus Z3. Z3 is equal to H2. So, P3 by rho g is equal to Pa by rho g minus H1 plus H2. So, that means P3 by rho g is less than P atmosphere by rho g. So, it is less than atmospheric pressure. So, here we will have a pressure which is lower than the atmospheric pressure.
That's why we have to suck that thing and then
yeah.
go up and
So, first you have to suck the air and okay. Now, if I make H2 larger and larger, so what will happen? It will be lesser and lesser compared to the atmospheric pressure.
so every time it will not come.
No, at one time what will happen, that this liquid at the given temperature, this pressure will be below the vapor pressure. So, evaporation will start. So, a vapor lock will be, a vapor bubble will be created and that will lock the flow. Flow continuity will be, will be lost and we will not have the fluid flow. That is what happens in case of pumps also or in case of turbines also. Okay. But there what happens, that we have a very high kinetic energy. That means we have a very high velocity head, that is why we are having a very low pressure head. But here what I am doing, I am having a very high static head, that is why we are having a low pressure head. Okay. So, this is the first, case 1 where I have neglected the friction. So, case 2, friction is considered. So, we consider friction. If we consider friction, then what we will get, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So, first part of the problem I am doing again with friction. That means, I am trying to determine Q when friction is considered. So, again just like the first case, P1 and P2, they are atmospheric pressure. So, they drop. This is negligibly small and this is equal to 0. So, and this is equal to minus H1. So, basically V2 square by 2g is equal to H1 minus HL. Again this is H1 minus F L by D V square by 2g. I know the formula I have written. Okay. So, H1 is known to me, L, D is known to me, F is not known, of course V1, sorry V2, V2 I have to determine. Now the problem is F is a function of V2. Please try to understand, F is a function of V2. Unless I know V2, I cannot find out F. Unless I know F, I cannot find out V2. So they are interconnected, and I have to have some sort of iterative solution. Iterative solution is needed as V2 is, sorry, as F is dependent on V2. Iterative solution is needed as F is dependent on V2. All right. So what are the steps? Assume a value of V2. First you have to assume a value of V2. Okay. Calculate RE, calculate Reynolds number. Okay. Let us say this is calculate F. So either this is 64 by RE or Moody's chart. Okay. Then calculate V2 from the equation, or let us call it V2 bar from the equation. If V2 is approximately equal to V2 bar, V2 bar, then V2 is the required velocity. Otherwise, replace PLACE, replace V2 by V2 bar and go to 1. So then you repeat this. Okay. So this is how most of the problems where F is head loss is involved, we have to do, because we will see that unless we know velocity, we cannot find out head loss, sorry, friction factor, and again friction factor is needed for determining velocity.
But normally we should assume which type of velocity?
Normally what happens, practical flows are in turbulent. So we will assume
Above 2000.
above that we will assume.
Not a round number, velocity.
So actually I will tell you. Suppose for this problem, what I can do, this term I can first neglect. I will get some sort of a value of V that could be our guess value. Yeah.
So neglecting the F into LD part.
Yeah. But that could not be whatever I have told. Whatever I have told, that could not be a general guideline. So there are some other problem where we cannot do that. But for this problem, we can do this, because I'll tell you, definitely this head is much larger compared to the head loss term. This is our H1. So sorry, this is our H1. Okay. And this is much larger compared to the head loss term. Okay. let me do another example. Let us say we have got two reservoirs. We have got two reservoirs. The height difference between the reservoirs is capital H. And then this length is L, and the diameter of the pipeline is D. So, here again we want to know what will be the flow rate. So, this is a problem of hydraulic network, and it is similar to some sort of electrical network, though it is a very simple network, only one element is there, but it is similar to an electrical network. Okay. So, we can take the analogy and do the problem, but we can do it using Bernoulli's equation also. So, if I use Bernoulli's equation, I will take one point here, I will take another point here, and I can write Bernoulli's equation between these 2 points. That means P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So, again these two pressures are same. Okay. These two velocities are negligibly small. Okay.
This one, how you are concluding the velocity part? Depending on the what we are concluding, that is very small.
Actually, these reservoir areas are very large. So, that is why we are telling that they are negligibly small. So, just I am putting 0 approximately. So, Z1 minus Z2 is H. H is equal to HL is equal to F L by D V square by 2G. Here again we have got the same problem. That means, first you have to assume the value of V, and then we have to see whether it is matching or not. Okay. So, this is how this problem can be done. Well, what I was telling, that this pipeline problem, they are similar to, or they can be reduced to some sort of electrical network problem. Like we have got a pipeline where we have got pipe elements like this. So, this is element 1, this is element 2, and this is element 3. So, we can assume that there are 3 resistance R1, R2, R3, and they are all in series. Okay. They are all in series, and the equivalent resistance R will be R1 plus R2 plus R3. Similarly, if there are 3 pipelines, one is like this, one is like this, and one is like this, and they are connected, let us say, by some header. So, here again this is R1, R2 and R3. So, these three are in parallel, meaning that all are having the same head. Only thing is that flow rates will be different through these pipelines. Okay. So, just like our electrical network, we can do the analysis. Okay. So, that we can do in this case, and actually
And the quantity will be resistance dependent.
definitely. So, let us say if we take up a problem like this, that we have got a pipeline, we have got a pipeline, and then from, let us say, some distance we have laid a parallel pipeline, both are going to the same reservoir at same level. In a two-dimensional diagram, it may appear that it is going to different level, but it is going to the same level, that is, they are having same length. Of course, it does not matter if it has different length. Let us say again we are having the head difference is equal to H, head difference is equal to H. So, we are interested to determine how much fluid will be transported this pipeline system. So, basically here what we are having parallel here and series here. Let us say all these are different pipelines. Let us say it is L1 D1, L2 D2 and L3 D3. So, L3 D3. So, we want to find out what is the flow rate from reservoir 1 to reservoir 2. So, how can we do this problem? We can consider what is the total resistance, and from there we can determine what is the flow rate. But if you try to solve this problem, just think over it, it involves lot of iterations. Okay. So, it involves lot of iterations, and then of course, again all these iteration, in case of any iteration, it depends on how intelligently we had the initial guess. So, if we have made so if we have made a good guess, so obviously within a few cycle we will have it converged, otherwise we have to go for number of cycles. Similar problem we may numerical problem we may take up when we will have the tutorial class, and we may discuss this. So, I think that is the end of our discussion for fluid mechanics. Still we have got some time, so let us start our refrigeration and air conditioning. So, I think well, refrigeration, that is creation of low temperature or creation of cooling effect. Though we can use the same principle for heating also with the help of heat pump. But in general, refrigeration means that we are extracting heat from some sort of a low temperature body. Okay, we are extracting heat. The basic principle of refrigeration, we can start from the reverse Carnot cycle. We can start from a reverse Carnot cycle. So, if a Carnot cycle can be used, that is the ideal cycle for heat engine cycle, then a reverse Carnot cycle that can be used for as an ideal cycle for refrigeration. So, a reverse Carnot cycle, if we have the TS diagram of a reverse Carnot cycle, let me write it. If we have the reverse Carnot cycle and TS diagram of it, so we will have these 4 points and 4 processes. So, 1 to 2 we will have isentropic expansion, sorry, isentropic compression. Then 2 to 3, what we will have? Isothermal heat rejection. Then 3 to 4, I will have isentropic expansion, and then 4 to 1, I will have isothermal heat addition or heat absorption. Isothermal heat absorption. So, these are the 4 processes I will, sorry, I have, this should be the other way. Okay. These are the 4 processes. So, we can see the direction of the processes are just the reverse of our Carnot cycle for heat engine. Okay, forward Carnot cycle or Carnot cycle for heat engine. Now, I can diagrammatically represent it like this. Basically, it is T2, this is T1. So, let me write it, this is T1, this is T2, and we need some work to run this. So, this is your refrigeration cycle. Okay. So, it is between 2 temperature limits T1 and T2, and well, we will have COP of refrigeration, coefficient of performance of refrigeration. I have already, so COP R I will have desired effect produced by the energy input, not heat input, by the energy input. So, energy input is equal to W, and desired effect produced, I am taking certain amount of heat which is Q, Q2, let us say Q2, this is Q1, so Q2 by W. So, I can write Q2 by Q1 minus Q2, and for Carnot cycle, for reversible cycle, I can write T2 by T1 minus T2. Well, so I do not want to discuss regarding heat pump, but the same cycle can be used as heat pump cycle, only the COP definition or COP expression will be different. Okay. Otherwise, same cycle can be used as a heat pump cycle. Yeah, yeah. And nowadays actually the heat pumps are becoming very prominent because of energy recovery and other usage. So, same cycle can be used. So, so we can see that in principle a Carnot cycle can be used as a refrigeration cycle, and obviously it will give you, for the given temperature limit, it will give you the highest COP. Then what is the problem of Carnot cycle? Why we cannot use Carnot cycle as a practical refrigeration cycle? So, let us see that. So, limitations of Carnot cycle as a refrigeration cycle. Now, the type of cycle means the Carnot cycle. Let us say we are using Carnot cycle, but we can use different type of working substance. We can use a two-phase working substance, where there is change of phase during the cycle, or we can use a gas as the working substance for Carnot cycle. Let us see these two cases separately. So, if we use a two-phase working fluid for Carnot cycle, for reverse Carnot cycle. So, we have got TS diagram, we have got this two-phase dome, any arbitrary fluid in two-phase situation, and then we have got so 4, 1, 2, 3. Okay. So, I have explained the Carnot cycle. We will have two isothermal heat transfer processes, one heat addition and one heat rejection. When I am having a two-phase working fluid means the fluid there will be phase change. So, these heat addition and heat rejection processes are easy to achieve. They can be achieved as a boiling process or a condensation process. Okay. Here we can see this is a condensation process and this is an evaporation process. So, we will have the condenser here, we will have an evaporator here, and these two are adiabatic, reversible adiabatic expansion process and compression process. So, this is reversible adiabatic expansion process, this is reversible adiabatic expansion process. All right. So, now here what we can see, we are compressing a mixture of liquid and gas or liquid and vapor, and we are compressing it such that at the end of the compression we are getting saturated liquid only, and here we are starting from the saturated liquid, we are expanding so that we are getting a mixture of liquid and gas, that too mixture of liquid and gas at a fixed proportion, at a given proportion. So, both the expander design and the compressor design becomes very difficult. Practically, we cannot design such type of expander or compressor. Okay. And in a compressor, we know that in any practical compressor, if we have this type of design, so yeah, liquid refrigerant, that will that will I mean collide with the valve and the piston head, and it will make pitting and damage and all these things. So, there is this difficulty, and in this case also this type of expander design is almost next to impossible, we cannot do it. So, that is why we will not be able to operate this thing as a Carnot cycle, reverse Carnot cycle. And that too, if we design this type of thing, we will see that lot of work input is needed. Okay. So, we will not be able to do this. Now, in case of gas, if we design this, that we have got a gas and we have got this four, 1, 2, 3. So, what happens in case of gas when it is a single phase fluid? Isothermal heat addition and isothermal heat rejection, that becomes impossible. Whenever we add heat or whenever we reject heat, so there will be some temperature gradient across which heat transfer will take place. So, this becomes very difficult. That is one thing. Another thing also, we will have lot of energy expenditure for the compression of the gas. So, we will have very which
very large condenser.
yeah, we will have no, here there is no concept of condenser, because here we are taking gas only. Here we are taking gas only, but what we will have to create some sort of reasonable refrigeration effect, we have to spend lot of energy. So, first thing is that isothermal heat addition and isothermal heat rejection we cannot realize. Then, if at all we can make some sort of a cycle, so to create some sort of reasonable cooling effect, reasonable refrigeration effect, we have to spend lot of energy. Okay. Or we will have very low COP. Okay. See, what you have told is correct in a sense that here we will not have condensers or evaporator, but some sort of heat exchanger we will have. Those heat exchangers will be very large. Those heat exchanger will be very large. And as I have discussed earlier, that here we need isentropic expansion and isentropic compression. So, here the process should be very fast, and here we need isothermal heat addition and isothermal heat rejection. Here the process should be very slow. So, in a cycle, part of the processes I need it to be very fast and part of the processes I need to be very slow. It is difficult to design. So, we can see that both for vapor as the working fluid and for gas as the working fluid, Carnot cycle or reverse Carnot cycle is not the good candidate, is not an ideal candidate for refrigeration, just like it was not a good candidate for heat engine cycle. So, we have to look for some other cycle and in the next class we will see what type of modification in Carnot cycle will give us good result.